Now, what if we have a function that passes through the x-axis, and we will need to find the total area of this function? So you will notice that the area ABC, we denote this as A1, and the area CDE, we denote this A2. From our area ABC and constructing a rectangle here, we can generate a differential area in which we have a differential area of 1 is equal to y dx. And applying the integration, we will have the area 1 integral of y dx evaluated from A to C at this point. Then the next step is to construct a rectangle here. The rectangle of A2 is dx and negative y, in which we will have a differential area of 2 is equal to the negative y dx. And applying the integral sign in both sides, we will have A2 is equal to the negative integral of y dx, evaluated from C to B. Now, the next step is to add these two areas in order for us to find the total area of the curve, in which we will have A1 plus A2, in which we will have the area of the integral of y dx evaluated from A to C minus the integral of y dx evaluated from C to B. Now, this is the concept of finding the area in this case. So we have here an example that we now need to find the area of the curve y is equal to x cubed, and it is bounded from negative 1 to 2. Now you will notice that our function y is equal to x cubed is an add function. So we are to expect that our graph will look like this. In order for us to clarify this assumption, we will need to set a table of values of x and y. Now, if we use the bounded region, that is negative 1, if x is negative 1, then y is equal to negative 1. If x is equal to 0, then y is equal to 0. And if x is equal to 1, then y will become equal to 1. And if x is equal to 2, then our y is equal to 8. And with this table of values, we can construct our graph that is now by plotting our points or our coordinates, we have the negative 1 and negative 1, 0, 0, 1, 1, 2, 8. And tracing the curve, that is, so the curve will look like this. Now, pardon my drawing, but you can check your solution by visiting some graphing calculator, or in my case, I usually prefer this site. You can check the description and visit this site, in which our bounded region is this: x is equal to negative 1 and x is equal to 2. And notice that we have two areas that under the curve of our function, in which this will become our area 1 and this will become our area 2. By constructing a rectangle, we will have a base of dx, length of negative y. The other area is dx and y. Now, from these differential areas, we can formulate our formula, in which our area or our differential total area is equivalent to the differential of area 1 plus the differential of area 2, in which we will have, applying the integration, we will have the area is equal to the area of this is negative y in which we have a negative sign here. Since our y is a negative, then negative y dx evaluated from negative 1 to 0 plus our differential area 2, in which we have the integral of y dx evaluated from 0 to 2. As I said that we will need to equate our y here, then our area will become to equal to negative integral of x cubed dx evaluated from negative 1 to 0 plus the integral of x cubed dx evaluated from 0 to 2, in which we can evaluate the integral of x cubed, that is equal to 3 plus 1 is 4, so 1/4 negative x fourth evaluated from negative 1 to 0 plus 1/4 times x4 evaluated from 0 to 2, in which we will need to plug in the values of our upper and lower limit of integration, when we will have take this outside, negative 1/4 0 to the 4 is 0 minus negative 1 to the 4 plus 1/4 multiplied by 2 to the 4 minus 0. Simplifying, we will have negative 1/4 times 0 is 0. This will become positive 1 times negative 1. Due to the negative 1/4 outside of the brace, we will have a positive 1/4 plus 2 to the 4 is 16 divided by 4 is 4. Applying the lowest common denominator of 4, there is 1 plus 16, in which our total area is equivalent to 17 over 4 square units.